Welcome back. So we discussed PID and we saw some examples of PID last time. Like if you take a field F, then the polynomial ring Fx over F was a PID. Today in this class, we'll discuss quotient rings. So let A be a commutative ring with 1 and I be an ideal in A. Then we know that A mod I, the set of cosets of. So we want to define the quotient ring, modular and ideal. Okay, so for group we define quotient modular subgroup. Here, as I said, the correct object in some sense. Although we will talk about subring, some sense more or equally important object is an ideal, and we are going to talk about quotient by an ideal. So A mod I is the set of cosets of the subgroup I of A. So if you have an ideal, then it's a abelian subgroup, and A is a commutative ring with 1. So A is in particular an abelian group, and you have a subgroup. So A mod I, which is the set of cosets of the subgroup I in A, because I is in particular a subgroup of the abelian group A. So we know it is an abelian group. And now you let that, this we already know. So now you take A plus I and B plus I two cosets. So you want to define a ring structure on this A mod I, right? So you have to define a multiplication. So you simply define A plus I, the coset, plus B plus I. So I'm denoting this because the ring has two abelian and multiplicative structure. I'm denoting the cosets as abelian, as AB plus I, okay, to distinguish it from the multiplicative structure. So A, I mean, if you like, is plus and dot a commutative ring. So AB plus I. So first thing again you need to check it is well defined. So suppose A plus I is also represented by coset C plus I. Then A can be written as, right, that precisely means that A can be written as C plus I1, and the coset B plus I, suppose it is written as D plus I. That means the element B can be written as D plus I2, right, where this I1 and I2 are in I. So, right, that's what this means if you go back to the definition. So, what happens to AB? If A is C plus I1 and D plus I2, then AB is CD plus I1, I2 plus C times I2 plus D times I1. But anything which has an I will be inside I, because recall what is the definition we have, that R times I belongs to I for all R in R and all I in I, right? So, so AB should be equal to CD plus, so AB will be equal to CD plus something. All of those elements will be in I. So I can write AB equal to CD plus I3. That means AB minus CD is an element of I. So that means the coset of AB plus I is same as the coset of CD plus I. Right? So this multiplication is well defined. Just simple checking. Once this multiplication is well defined, we immediately get that this is a commutative operation, the way it is defined, because A plus I into B plus I is same as AB plus I, which is same as BA plus I, because the ring is commutative. This is a commutative operation. This is an identity element is there, 1 plus I, right? 1 plus I is this identity element, 1 plus I. And you can check this operation is associative also. It's not difficult to check that the operation is also associative. So this is an associative commutative binary operation, this multiplication, A, namely this one, A plus I, and if you like some dot into C B plus I, you simply define it to be AB plus I. So this is an associative binary operation, identity element 1 plus I. So then R plus I is it was already an abelian group because I is an abelian subgroup. So R plus I with respect to coset addition and this coset multiplication forms a commutative ring with identity. Okay. So this is the structure of, this is the definition of quotient ring. So we had quotient group, now is a subgroup, abelian group, quotient group. And now we have that if you take the definition of ideal, and you can check that the ideal is necessary here, that you need this kind of property. Excuse me, that if R times I will be in I for all R in R and I in I. So this is needed, the definition of ideal, okay? So you can check it. So this is anyway. So this is so whenever you have an ideal, then we have this definition of quotient ring. Okay. So next is uh, excuse me. So next is so this is about quotient ring. Next is about ring homomorphism. So again, like group homomorphism, if you have two rings, let's say A with binary operation plus excuse me, A comma plus 1 binary operation on it, and dot 1 multiplicative another binary operation, second binary operation on this with respect to which this is a ring. So A plus 1 is a subgroup, and A dot is a associative commutative binary operation with identity element. B has a binary operation plus 2 with respect to which it's an abelian group, and B had a second binary operation dot 2 with respect to which it is associative commutative and has an identity element. Then again, a map is said to be a ring homomorphism if f of a plus b, where this plus is plus 1 with respect to your a, it gives you fa, and its addition with plus fb. This plus is the second operation. So it's just the definition of group homomorphism. So this means it's a group homomorphism, abelian group homomorphism, which you already know. And the new condition is f of a dot b, it should be fa dot fb, where this dot is inside a and this dot is inside b, right? So if there's two structures, then it should be those mapped with respect to the first structure. Since it's abelian group, a ring homomorphism, first of all, should be abelian group homomorphism. So this is the condition for that. And second condition is it respects the multiplicative structure. And as before, a ring homomorphism is said to be an isomorphism. So if there is another ring homomorphism G to B from B to A, such that G composed F is 1 on A and F composed G is 1 on B, and this condition happens. So if there is another map, another ring homomorphism from B to A, such that G composed F is the identity on A, F composed G is the identity on B, and you call it a ring isomorphism. And this happens if and only if, again, like in group homomorphism case, it's a ring homomorphism, and if F is a ring homomorphism plus F is injective and F is surjective. So if and injective can be checked if and only if kernel equal to 0. So this is further, this is same as kernel F equal to 0. Okay, so kernel F is again the so kernel F. Okay, so what is kernel F? It is the set of x in A such that f of x equal to 0 B, right? So this is this is equal to 0 if and only if injective means kernel of the ring homomorphism is 0, just like in the previous case. And if it is injective and surjective, then you can construct an inverse and ring homomorphism. So this condition is satisfied. So if F is a field and theta from, so what happens in the special case of a field? Okay, so this is the definition of ring homomorphism. Then we said that ring homomorphism is injective if and only if kernel is 0, and uh, uh, so where kernel F is the set of elements which goes to 0. So there are two identity elements, but kernel definition is still same. Those, it's additive identity. So 0 is the additive identity. Those elements which goes to additive identity. You can check that this is the ideal. If x is in kernel and y is any element of R, then f of x times y is fx times f of y. So 0 times something, which will again be 0. Okay. So you can check that kernel of f is an ideal in this thing, in your ring A. Okay, so what happens in the special case if F is not a ring, F is a field? So if F is a field and theta from F to B is a ring homomorphism, where B is a ring, okay? So then where B is a ring, then kernel theta is an ideal in F, and kernel theta is, so kernel theta, as I said, one can check, this is the definition. So kernel theta is an ideal in F, and kernel theta is equal to 0. So kernel theta is an ideal in F. Now we have taken the special case where F is a field, and we are looking at this kernel of ring homomorphism, right? So kernel of the ring homomorphism, as I said here, you can check it's an ideal, because if x is an element where fx equal to 0, and if you take any element y in R, then f of x times y will be equal to fx times fy, but f of x equal to 0, so it will be 0 times f of y, so it will be 0. So any element, if it is there in kernel and you multiply by element in the ring, then still is in the kernel. So it's an ideal. So this is easy to check. So this part is easy to check. And so in a field, what are the ideal? I have discussed this. Ideal is either 0 or ideal is the whole of field. There are only two ideals, either 0 or the whole field. So if kernel is whole ideal, that means what is the image? Image is exactly 0, right? There is the image is exactly the identity, additive identity element B. So if that is the case, and otherwise, if that is the case, it's fine. Otherwise, if the map is not identically 0, then there is only option that kernel theta is 0. So kernel theta 0 means it is injective. So if a non-zero ring homomorphism is there from a field to another ring, then where f is the field, then it is always injective. Either it is injective or it's identically 0. So there's some fact which we'll use later. So ring homomorphism from a field is either injective or identically 0. Okay, so next is a non-empty subset of a commutative ring with identity is said to be subring. So we so far discussed the definition of ideal, but we also want to define subring at this point. So a subset of a commutative ring is said to be a subring if, with respect to the same addition and multiplication, it forms a commutative ring with identity. Okay, so here the thing is we insist, like most books, that ring should have identity. Okay, so in our definition, for example, okay, so for example, R plus is a subring of C plus dot, right? The set of real numbers is a subring of the set of complex numbers. Or set of rational numbers, similarly, Q plus dot will be a subring of R plus dot, right? These are some examples. Or R plus is a subring of C plus dot. Note that 2Z is not a subring of Z because we insist on identity. So one doesn't belong to, excuse me. So one doesn't belong to 2Z. So 2Z is not a subring. Okay. Subring must contain 1. So now we have the isomorphism theorem that if f from A to B is a ring homomorphism, then kernel of f is the set of x in A if f x is identically 0. As we said, this is an ideal. And what is the image of f? Image of f is again f of x, so that x is in A. So it's just the set of fx. So this also we discussed before, have discussed before. So this is a subgroup of the abelian group B, and A is a, so we are all taking all rings are commutative. So here we are not saying it, but just for simplicity, we'll take both to be commutative. So anyway, we don't strictly need it, but we'll assume it. But so the kernel will be is an ideal in A, and we have A mod kernel of F. So if you have ideal, we can consider the quotient ring. Then that is isomorphic to the image of F. Okay, and this proof is exactly identical to the proof we have given in the case of group. We have proven this, that if you have a group homomorphism, abelian group homomorphism A to B, then A mod kernel of the group homomorphism is isomorphic to image of the group isomorphism. So you already know this is an isomorphism. So this one we already know it is an isomorphism of abelian groups, and you check that this actually also respects the multiplication. So it's a, this is a ring homomorphism, then anyway it is injective and surjective, so it's an isomorphism. Okay, so you just check that the map we have defined this way takes A plus I into B plus I to AB plus I. Okay, and that is not difficult to, wherever this map takes A plus I into B plus I, it also takes AB plus I to the same element. But I is kernel of it, and that is not difficult to show. Okay, so one can prove this. So I'll leave the proof for you. So let me, in this class, let me end with one example of this. So for example, you have the ring R it's a field, and you have the polynomial ring in one variable. So set up all polynomials with real coefficient Rx, and from here you can give a map to C, the complex numbers, by sending. So actually, if you think about a polynomial, if you are sending fx to somewhere, then that is determined by where you are sending x to. For example, you say take x to I, where I is square root of -1, right? So then fx goes to f, or in other words, you said fx to fi. So if you have a0 plus what it means a1x plus a(n)x to the power n, this gets into a0 plus a1 iota plus an iota to the power n. So f of x goes to f of iota, right? This is f of iota, a0 plus a1i plus ani to the power n, right? This is the map. So it's just enough to say x going to I. You see, we have just replaced x by I. So this is you can check that this is a ring homomorphism. You can easily check. So if fx goes to f of I and gx goes to g of I, then f plus gx will go to f plus gi. Fx times gs will go to fi times gi. So this is a ring homomorphism. Okay, that's not hard to see, and it is also subjective because if you have a plus bi, okay, this is subjective because this is a surjective ring homomorphism because a plus, so you have a plus xb goes to a plus bi. Any complex number is of the form a plus bi where a b are in R, right? So that is captured by a plus xb goes to this element, right? So that means this is a surjective ring homomorphism. Okay, so this is clearly a surjective ring homomorphism. Homomorphism. Okay, it's a surjective ring homomorphism. And but by this thing, Rx by, if I call this my phi, Rx by kernel of phi is isomorphic to C. Now I'm claiming what is the kernel. So you can see that x goes to iota. So x goes to iota. So x square goes to -1, or x square plus 1 goes to 0. You can check, right? You evaluate if x square plus, where does x square plus 1 go? X square plus 1 goes to I square plus 1, which is -1 plus 1, which is 0. So x square plus 1 goes to 0. On the other hand, if some element goes to 0, then uh, x plus I divides it, right? F of I, if f of I equal to 0, what does it mean? That x minus I is the root of fx, no? So if x minus I divides fx in cx, right? Because x minus y, this polynomial is not defined over R, it is defined over C. So x minus I divide fx, but fx is a real polynomial. So if I take complex conjugation, x minus I will also divide fx. Because fx is a real valued polynomial. So if x minus I divides fx means x minus I bar will divide fx bar in cx. But fx bar equal to fx because x is real value. So x minus I and x plus I both divides fx. So f bar x equal to fx. So that means x minus I into x plus I, which is x square plus 1, will divide fx. That is in Cx, but x square plus 1 and fx both are in Rx. X square plus 1 will divide actually fx in Rx. You can check. Okay. So the kernel is actually x square plus 1. So we saw that x square plus 1 goes to kernel, and so x square plus 1 goes to 0, and any polynomial x square plus 1, any multiple of that will go to 0. Conversely, if some polynomial goes to 0, then it is divisible by x square plus 1 in Rx. So kernel of phi is set of all multiple of x square plus 1. That precisely means this is the ideal generated by x square plus 1. What is the definition of ideal generated by x square plus 1? This is nothing but So this is x squared plus 1 into fx, where fx belongs to Rx, right? It is this set. This is the ideal generated by x squared plus 1 in Rx. Okay, so maybe make some space here. Okay, so as I said, this ring homomorphism is also surjective. I have already said that. And we get that Rx by x squared plus 1 is isomorphic to C. Right? So this is Rx is a ring, and if you divide by this ideal generated by this, this is the kernel. There's a natural map, this is the kernel. So this mod this is isomorphic to this field. So this is a field. Okay, so this is an ideal such that you quotient by this, it becomes field, and I give you the map and show that it happens naturally. Okay, thank you very much. So we'll continue next time.